Good evening. Today we will see one again problem which is of continuous beam and that is of floor beam. So we have this ABCD same plan we have taken. In last case we have with this beam we have designed in last video. And now in this video we are going to design this ABCDE this beam. So we have data same. So have width 230, slab carries floor finish as 1.5 and superimpose load 4 kN per meter square M25 Fe415. Now we have effective span maximum. If you will see in these all four, we have this 4 plus 2.6. So we have this at 6.6 meters. Maximum span we have 6600 mm. Trial depth we have taken L effective by 15. Now why we have taken L effective by 15? Now if you will see the diagram, in this diagram we have load on one side, we have load on this side, we do not have load on this side. So depth required will be less if than the depth required when we have load on both sides, and therefore it was taken as 15, and we will have a 440. So 440 plus 40, 480. So we will provide overall depth 480 millimeter and small d we have 440 millimeters. Now load calculations, load from slab plus weight of wall, self weight of beam, same we have. Now we have in this two-way slab and we have load transferred in this way. Now on AB we have this triangle, so we have triangular load on this. If we will go S4 again we have two-way slab, so we have trapezoidal load over here. S5 we have one-way slab, so half load will be on CD beam, and S7 we have two-way slab, and then we have again triangular load on this. So loading we have in this fashion. S3 we have triangular, S4 we have trapezoidal, S5 we have one-way slab, and S7 again we have triangular load. Now we will calculate one by one. Self weight of slab we have 25D. 25 into 0.41, 3.5 kilonewton per meter square. Floor finish 1.5. So total load we will get it as 5 kilonewton per meter square. Now load on beam AB. So now we have it as a triangular load. So we have WLX by 3, 5 into LX we have 4, by 3 we have 6.67 kilonewton per meter. And weight of wall 20 B into H. Floor to floor height is 3 meter. And depth of beam is 0.48, and therefore we will get this value as 20 into 0.23 into 3 minus 0.48 and 11.59 kilonewton meter. Self weight of beam 25 into 0.23. Now 0.48 minus 0.14, because we have this as depth of slab, and we have to subtract from overall depth of beam that depth of slab which we have already considered in first, where we have dead load from slab, and we will get 1.96 kilonewton per meter, and therefore total dead load we will get that is 6.69, 11.59, 1.96, that is 20.22 kilonewton meter, and factorial load we will get it as 30.4 kilonewton per meter. Now this load we have that is on AB. Now we will switch over to live load. We have again triangular, so 1.5, this is to make factorial WLX by 3, and then we have that is equal to 1.5 into 4 into 4. We have 4 load, live load, and 4 we have span, and we will get this value that is equal to 8 kilonewton per meter. We have this value. This is again on beam AB. So AB we have 30.4 as dead load and 8 as live load. Then we have load on BC. Now I will not go in detail. You can see this WLX by 2, 1 minus 1 upon 3 beta square. And from this we will get 6.1 kilonewton per meter. Then weight of wall we have same. Self weight we have again same, and we have total factorial dead load 29.5. So this is on BC, and factorial live load we have 7.3 kilonewton per meter. Now we will switch our load on CD. So we have one-way slab, and then dead load from slab to beam WLX by 2, half we have directly on beam CD. So 5 into 3 by 2, 7.5. Weight of wall same, self weight we have same, and then total factor-head load we will get it as 31.6 kilonewton per meter, and factor-head live load we have 9 kilonewton per meter. So 1.5 to make factor-head, 4 we have W, and span we have Lx we have 3, and then upon 2 9 kilonewton per meter. Now load on beam CD again triangular, so WLX by 3, other values are as it is, and then we have factor-head dead load 30.4 kilonewton per meter, and factor-head live load we have 8 kilonewton per meter. So now we know dead load and live load. We will prepare a table and we will write the values for A, B, B, C, C, D, and D. Already mentioned we want dead load and we want total load. Because load combination we have dead load and we have total load. Live load we do not have, only live load in combination. So we have these values, you can see these are dead loads we have on A, B, B, C, C, D, and D. Then if we will go to live load, we have these values of live load 8, 7.3, 9, 8. Then we have total load on beam, that is dead load plus live load. So we have this value. Now we have to find out bending moment due to dead load. We have to find bending moment due to total load. So WL square we have bending fixed end moment, because this value again we are going to calculate by using WL square by 12. So this value we can have W 30.4, effective span we have 4. So W 30.4 into L square by 12. And we have this value 40.53 kilonewton meter. So likewise, we are in position to find all values 38.4 into 4 square by 12, and we will get 51.20 kilonewton meter. So likewise, we have to find all these values, and after this we have to go for load combination. Now you can see we have stiffnesses. So now this BA as farther end is simply supported, so we have taken value 3 EI upon L. So it goes to 0.75. Then BC continuous, so 4 EI by L. CB continuous, CD continuous. So all these are 4 EI upon L, and D again simply supported farther end 3 EI upon L. Then at joint B we have total stiffness 1.75, at C 1.61, at D 1.36. And then we have stiffness of member upon total stiffness. So 0.75 divided by 1.75, we will get 0.43. EI 1. So nothing is there, means 1, we have 1 upon 1.75, 0.57. So likewise, now we have 1 EI. So 1 upon 1.61, 0.62, 0.61, we have 0.38. Similarly, 0.61 upon 1.36, 0.45, 0.75 upon 1.36, 0.55. So likewise, we have these distribution factors. And now we will go bending moment calculations. Now maximum span moment AB and CD. So now we have to find AB, then we have dead load plus live load on AB, then we have alternate. BC we have only dead load, CD dead load plus live load, and D we have dead load. So automatically we are going to get span moment on AB and CD at a time. So now we will put the values in this. So we will have this total load 38.4. This is dead load. This is total load, and then this is dead load. And then we can have distribution table, moment distribution table. So we have distribution factors 0.53, 0.57. As we have seen, we have joint B, joint C, joint D, and then we have E. So we have to release support A and E because these are simple supports, and therefore we have this as minus 51.20. So this should be plus 51.20, and half we have transfer on this to 25.60. This is 40.53, so it goes minus 40.53. We will have this minus value, and then we have distributed at B. We are going to add these two, take opposite moment, and then multiply this moment by 0.43.57. So these values we know, which will give me final moments. 60.69 at support B, 106.32 at support C, and 104.82 at support D. Now we are interested with AB maximum moment. So we have this same way we have to calculate. We have to find out point of zero shear force, And knowing point of zero shear force, we can find maximum moment. So we have 49.46 kilonewton meter. Similarly, we will find CD because we have same loading for CD also. And then by taking moment about D0, then we can have a shear force 0 point. And knowing this, we can find maximum span moment, which will be 115.51 kilonewton meter. Now we can have same loading for BC and D. So we can have this total load on BC and D and dead load on AB and CD. And then in the same way, we have to calculate these values. And by calculating these values by using moment distribution table, we are going to get support moments. And then we can find support more. Knowing support moments, we can find shear force 0 point. And by knowing shear force 0 point, we are in position to calculate maximum bending moment, and that is 1.33 for BC. Now go for DE, then we are going to get again shear force 0 point for DE 2.64 gives me maximum span moment 35.49 kilonewton meter. So likewise, we have this span moment AB, BC, CD, and DE. Now we will go to maximum support moment B. We have to apply total load on AB and BC, and dead load we have on CD, and total load we have on so total load on AB and BC and dead load on CD and D. Then we will get these values. So actually we have to consider only B support, and then we have to find out. So we need not require to go for this. So if you do not show these also, then also it's okay. And then we are going to get this value maximum support moment 64.88 kilonewton meter. Now similarly, you can go to support C. So we have support C likewise, and then from this we will get moment at support C 110.02 kilonewton meter. And similarly support D, we have adjacent span, we are going to get value that is equal to total load, and then we have dead load, and we will get 115.62 kilonewton meter, which is at support D. And then we will write it support A, B, then span moment, and then we will get values in this way. You can see we have AB span moment 49.46, support moment 64.88, BC support moment at B 64.88, span moment 1.33. Support C 110.02. Similarly for CD, then we have maximum span moment 115.51. Then support moment we have 115.62. So these are very close values. Then support D again same value. Span moment we have 35.49, and this is 0. So this is the table which will gives you total idea about the moment. And then we can have in the same way depth from bending moment consideration. Then we have RU max 3.45 for M25 FY 415, and then we have this value 115.62. Now try to understand, we have to always consider maximum moment, and we have that is 115.62, which is at support, and at support we have tension at top, so beam will act as rectangular beam, and we have width for this rectangular beam we have considered 230 millimeters, and therefore we have this value 381.72 required, which is less than 440, therefore okay. Then reinforcement for span AB, so we have to substitute the values of the moment. So we have to find value of X, which will gives me value of BF, which will be L0. We have 3.14. Here we have calculated bending moment 0 point. So somewhere we have that is at 3.14, and that will be my value of L0. L0 by 12 plus 3 DF plus BW is 911.67, and then we will substitute this value, gives me AST 315.62 millimeters square. So we will provide 1 bar of 12 and 1 bar of 16. Generally we have to provide same bars over here, so it is better. Theoretically we can have, practically is not possible. We can go directly 2 bars of 16 torque, that is preferable.